All right, so let's get started. Looking at this warm-up, right? Hopefully you had a chance to attempt this before I get started on this. Okay, find an equation of a line tangent to the curve at the given point. So the curve that they're talking about is this right here, this function right here, right? And they want us to write an equation of a line that's tangent, and that's in this hint right here. Some of you guys might not have done this since IM1, right? Or Algebra 1, wherever it was. Equations of a line can be written either using point slope form, right? Point slope form, or slope intercept form, slope intercept form. So either one of those forms are fine. Both of those are equations of a line, right? And that's the part that kind of seems tricky because it's like now we're combining this stuff from IM1 with the concepts that we learned in calculus, right? We have been working with this thing called the derivative. And some of you guys might not have gotten it down in your head yet that when you take a derivative of a function, you're finding the slope of a tangent line at any given point, right? The derivative just tells you the slope of a tangent line. That's it. That's all it is that a derivative does, right? So in calculus, if you don't know what to do, right, and you ever see the word tangent line in there, take the derivative of whatever function they're giving you, right? At least that right there will get you a point on a free response question. So don't ever leave it blank. Just say you don't know. You see the word tangent line involved. Chances are, since you're in a calculus class, you're going to need to take the derivative of it. So I have a function here, y is equal to x cubed plus 1 over 2x. I see that I need to write an equation of a line that's tangent. I'm going to go ahead and take the derivative of this. Okay? When you take the derivative of this, now we got to go into the calculus part of this. Understand that this is a quotient, right? This is a quotient. There is a low function, and then there is a high function, isn't there? There's a function on top, and there's a function on the bottom. Please make sure that you use the correct rules when you do this, right? You can't just take the derivative of the top and then put in the bottom the derivative of the bottom. This is not the correct derivative, by the way. If you write this as your derivative, you've already gone off the rails, right? You have to see that this is a quotient rule, and with the quotient rule, you get to say the fun phrase with this, right? Low d high. So low is 2x, d high is the derivative of the top, which is going to be 3x squared, minus high, whoops, that's x cubed plus 1, minus high, d low, derivative of the low is 2, all over low, all over low. Wow. Careful with that, knock me. There you go. That's your derivative. And if you are, I kid you not, if you're taking the AP exam, if you're taking my test, and you're asked to calculate this, and you just write that, right? You just write that. That at least gets you a point. In fact, if this was a 5-point problem, I'd give you 2 points just for the derivative, because not only did you know that you need to take the derivative, you took it correctly with the quotient rule, right? It sounds crazy. It's almost half the credit just for doing the derivative, because that's half the problem right there, is calculating the derivative function. Okay, the next point you could get from this is actually evaluating this derivative at the point we care about. Remember, this is a function that tells us what the slope of the tangent line is at any given x value. I care about it at this specific x value. So I'm going to go ahead and plug that in. You could simplify this out first and then plug it in. It doesn't really matter. You're going to have to simplify it anyways after you plug it in. So I'm going to just plug it in. I'm not going to simplify it yet. Actually, nah, you know what? I'm just going to go with it. Let's see here. So this is going to be 2 times 1, right? 3 times 1 squared minus 1 cubed plus 1 times 2 all over 2 times 1 quantity squared, right? So this is going to tell me the derivative of y evaluated at x equals 1. So that's going to tell me the slope. That's going to tell me the slope of the tangent line right there. This is essentially, this right here is equal to the slope of the tangent line at x equals 1. That's essentially what I'm showing right here. Okay, so we're going to go ahead and simplify this out and evaluate this. So I have here in the top, this is going to be 2 times 3, which is going to be 6, minus 2 times 2, which is 2 times 2 is 2 times 2 is 4, isn't it? Right? 2 times 2 is 4. And in the bottom right here, I'm going to have 2 squared, which is going to be 4 as well. So 2 minus 4 is 6 minus 4 is 2 over 4, which tells me that the slope that I have here is 1 over 2. if you guys could, let me know if I did anything wrong or did any calculations wrong. I kind of wrote that in my head. So if I did anything wrong, double check that for me. Or let me know if you got something different, right? That's what I'm getting as my slope. My slope that's going to go in for m is going to be 1/2, right? So my equation, Max, I got it. Well, you shouldn't be surprised. You're good. You're good. You guys just don't realize the terminology is a little bit different, but that's perfect, right? So to write my equation of a line, I already have this part that goes in for my slope, right? Now, the other part you need for an equation of a line is either the y-intercept or a point. I like doing the point. It's a little bit easier. It's a little bit quicker than doing slope-intercept form. Slope-intercept form, you have to plug in x and y and then solve for b. Point-slope form, you plug in your x and your y into the equation and you're done, right? So I have my x right here. That's going to go in for x sub 1. I need my y. Well, all you have to do to get your y value, right, is plug in your x value, right, into the function. So if x is equal to 1, y is going to equal to 1 cubed plus 1 over 2 times 1, right? All I'm essentially doing is plugging in 1 in for x to find out what the y value is going to be at x equals to 1. So the y value will be 1 cubed plus 1, which is going to give me 2, over 2 times 1, which is 2, which tells me that y is also equal to 1, right? Y is also equal to 1. So x is equal to 1, y is equal to 1. So here's my equation of a line. You ready? Here's my equation of a line. Y minus y1, which is this point right here, which is 1, equals my slope, which is 1/2, times x minus 1. And that's it. That's my final answer. And oh, yeah, but that's okay. Hopefully you will be able to see the recording and see if you missed anything. But you didn't miss much. I was just showing that you plug in the x value to get the y value. Once you get the y value, you have yourself a point, and add it on with the slope you calculated earlier. You're able to find an equation of a line that is tangent to the curve at the given point. And that's this equation right here. If you do it using y is equal to mx plus b, I like going from here and just working it out from here. So y minus 1, distribute the 1/2, like so, and then add the 1 over. You'll get y is equal to 1/2 x plus 1/2. And that's your second way of writing it if you want to use slope-intercept form. In calculus, they don't care which form it is. All they care is that you write down an equation of a line, and it doesn't matter which form it is. It could actually be this one or this one. Both check out okay. And let me just prove it to you by showing you a graph of this real quick. Let me prove this to you that that actually works the way it should. So let me go over here, open up my favorite graphing app, Desmos. You could also do this on your calculator, but I'm going to show you this right here. So let's say here, the function that we're dealing with was x cubed plus 1 over 2x. X cubed plus 1 over 2x. So it's a fraction, first of all, and it's going to be x cubed plus 1 over 2x. And it's this wonky looking graph right here. This is a crazy looking graph, isn't it? So when they want us to write an equation of a tangent line, right, at x equals 1, we found it to be this line right here. When we did our work, what did we get? We got y minus 1. So I'm going to write that in. Y minus 1 equals 1/2 times x minus 1. Check it out. The point that they're focusing on is that x equals 1, which is right here. And this line that we just wrote, this line right here that's in blue, can you see how it's tangent? It's only touching the curve right here at this single point. See that? If I keep zooming in, it looks like it's touching it at multiple points, but it's only touching right there at 1, 1. It is tangent at that point, and that's the tangent line right there. Boom, only touches this curve right there at 1 point. So that's it. That's it. That's it in a nutshell, right? That's how you write an equation of a line, tangent at a point. Not bad, right? Pretty neat. Today, though, I wanted to show you some more stuff that I want to continue what we'd left off on yesterday, right? Do you guys remember? You can actually do the derivative. If it's at a point, you can just do this on your calculator, right? Instead of doing the work of doing low D high minus high D low over low low and then plugging in the point, you know, your calculator can do this for you and it'll give you the same number. And I wanted to show you that right now. If you guys want to open up your calculator app on your on your Chromebooks, if you want to follow along with me, you can. Or if you have a TI calculator on hand, you can do that with me as well. Check this out, right? Some of you guys might not remember, but to get to the derivative part on your calculator, you can do the same thing. And all you have to do is press Math and go down to option 8. Math and option 8, which is the N deriv button. And I'm going to put that into your notes for you. But you see right here, it's the derivative, and then you get to type in the function that you want to take the derivative of, and then tell it evaluate it at a point. So if you want to do this on the TI calculator, you're going to go ahead and press the Math button, and then go to option 8, which is the N deriv option. When you do that, you go into here. The only thing is, though, you need to make sure you pay attention to the variables that you're using. In this case, I'm gonna just, if ever in doubt, just use X. It makes it easier that way. But there will be times when you use T, and just replace the T with an X. And you'll see what I mean when we start doing the other problems. But I'll have to start this off by telling the calculator, hey, I'm taking the derivative with respect to this variable, and that variable is the variable I'm going to be using to type in this function right here. Use parentheses when you do this, by the way. I know it already has parentheses, but use extra parentheses when especially when you're dealing with fractions. You never know if you mistype in a function or not. So you see here, x cubed plus 1. I'm putting in its own parentheses for that, and then I'm going to have that divided by 2x, right? 2x. And actually, to be even better about this, I should put parentheses around the 2x as well, just to make sure. You see that? And when I do that, it has its own bigger parentheses around the whole thing, telling me that I'm taking the derivative of that whole function, and I'm doing it at x equals to 1. You see that? So I'm doing that at x equals to 1. And when you type this into your calculator, it gives you an estimate of it. It's not perfect, right? It's not perfect, but you can round that, right? 0.499999995. That as a fraction is probably going to be close enough. It won't let me do it, to 0.5. Right, and 0.5 is what we got as our derivative, which is 1/2. They got 0.4999999 though. They didn't get exactly 0.5, but that's because the calculator here does a job of estimating it. Right, it estimates that slope for you. It gets close to it. And it isn't perfect, but it's a nice tool to use to calculate your derivatives. All right, so hopefully keep that open, and let's take a look at. Let's take a look at some more examples to do here, right? Let's take a look at more examples, and let's try using your calculator to do this, okay? So let's go on to today's lesson here. Let's see if we know how to evaluate, right? Evaluate derivatives at a point. Derivatives at a point. Let's take a look there, okay? So let's try this one right here. Let's try this example. Let's say I was asked, I was given the function f of x is equal to 3x to the 5th, right, times sine of x, okay? And I was asked to find the derivative at x equaling to 2.9, okay? And so I was asked to find the derivative at x equals to 2.9. Again, you can do this by hand. This is the product rule, right? We have two functions here. One function is 3x to the 5th. The other function is sine x. And we know the derivatives of those, right? Using the power rule and the trig rule that we have. But since it's asking us to evaluate it at a specific point, right, we could just plug this into the calculator, okay? You can just plug this into the calculator. And how do you know when should you plug it into the calculator? How do you know when you should do this by hand? And back before when we were taking the AP exam in person, you had two portions. One portion was a calculator active portion, and another part of it was a non-calculator active portion. So you couldn't do this with a calculator if you're on that portion. But if you're on the portion where you can use your calculator, I suggest you just use your calculator, right? If it doesn't say that you can't use your calculator, it says to do it by hand, you know, try just going with the calculator if you're just evaluating at a point, right? So I would just plug this into my calculator, right? So I would say that this is, going to be math. I go down to option 8. And option 8 is down here. Press N derivative, and I use this guy to calculate the derivative of this function for me, evaluated at 2.9. Okay? So and then I would go ahead and type this in. This would be x, and the function is this guy right here. I don't really need parentheses because it's just multiplying straight across. So I'm going to go ahead with 3x to the 5th times sine of x. And then, of course, this is evaluated at 2.9. All right, and I go ahead and just press enter. And I get this answer right here, which is negative 343.6399. Right, so I would say that the derivative evaluated at 2.9 is equal to this monstrosity of a number, negative 343.6399. And that would be my answer. No stress, no mess, right? No worries. Okay? And some of you guys are like, well, knock me, if this was a non-calculator section, how would I get this answer without my calculator? And then you would just do it by hand by doing the product rule, right? So f of x here is going to be equal to the derivative of the first, which is 15x to the fourth times the second, plus the derivative of the second, cosine of x, times the first, which is 3x to the fifth, right? So then you just plug in what you're evaluating at, which is 2.9. And this is the part that I would tell you right now. If you're doing this by hand, if you're on a non-calculator section, I would leave it here at 15 times 2.9 to the fourth times sine of 2.9, right? And right there, right off the bat, I would just leave it there because I don't know what sine of 2.9 is. The only times they ask you to do trig functions in your head is with the ones that are based off the unit circle. So they'll usually only ask you like sine of pi over 2, sine of pi over 3, sine of pi over 4, and sine of pi over 6, and all the other ones that are on that unit circle. If they do sine of 2.9, I don't know what sine of 2.9 is off the top of my head, and I'll just leave it there. Same thing with over here. This would be plus 3 times 2.9 to the fifth, right, times cosine of 2.9. And that would be it. This is, if I was doing it by hand, I would stop here. I wouldn't even bother, right? Will we have a problem like this on the test? Yeah. Were you just plugging into your calculator, or were you do it by hand? I don't know yet, okay? I don't know yet, but knowing the fact that if I ever ask you to calculate the slope of a tangent line, you can just take the derivative of it, evaluate it at a point, you do have a tool that will help you do that, right? You do have a tool that will help you do that. One thing I do suggest, though, is if you're doing one of these problems, I suggest you write down what you typed into your calculator, right? What you typed into your calculator. On a test problem, I would not go from here straight to here. If this was a test problem, I would write down that I was using my calculator. I was pressing math, right? The math button, and then I pressed the derive button to show that, derive button to show that that's what I'm using. And then I would actually write down on my test, hey, this is d dx of 3x to the fifth times sine x evaluated at x equals to at 2.9. That's what I have on my calculator. That's what I would show on my work if I'm using the calculator to evaluate it at that point. Just to show that this is what I typed in, just in case I did something wrong, right? I can still get partial credit, okay? I can still get partial credit. So maybe I typed it in wrong or maybe I typed it in, I did not get this number. By the way, did anyone try this and get a different number from my negative 343? There's a possibility that might have happened for some of you. If you are taking physics in particular, this probability is a lot higher. Because in physics, your calculator is probably set to degrees. In physics, your calculator probably is set to degrees, because in physics, you need it in degrees. In calculus, we need it in radians. So if I do the same exact problem, but I have my calculator set to degrees, check this out, you'll actually end up with a different answer. And that's actually a common mistake. That's actually a common mistake. So if you show me this part of the work and you got this answer instead of what I got, I can actually understand like, oh, your calculator was just set to degrees instead of radians, right? And then I can give you points still, just because I'm not going to mark you off if you're on the wrong setting. Does that make sense? All right, so it's always important to show your work whenever you can when you do these types of problems. All right, so here, guys, try this problem real quick. Okay? Use your calculator to do it, or if you want, you can try doing it by hand, but I really suggest you use a calculator for this. Here, try this problem out. Can you calculate the derivative of y is equal to x squared plus 2x over cosine of x evaluated at, right? Evaluated at x equals to 7, right? X equals to 7. So go ahead and try that. Type in your answer into the pear deck for me. Type in the answer that you get for the pear deck for me. I'm going to go ahead and put that screen on for you right now. And type in the answer that you get into the pear deck, and we'll compare answers. Let's see what you guys get. So hopefully that answered your question, Monica, about if you have a problem like that on the test. You might, and how to answer that. So I'm going to go ahead and set a 2-minute timer for you guys. Let's get into here. All you're doing is typing it into the calculator. Practice, practice, practice. Try it, try it, try it. See how you do on the calculator. Oh, what is this text message? All right. Minute to go. Let's see what answers we got here. Our answers are all over the board. They're all over the board. I've gotten, oh, good though. We have a good chunk that's around a specific value. Good, good. Oh man, but I've gotten some answers though. Did someone just accidentally type in 0? Someone just accidentally type in 0? Interesting. 2 people got the same. 3 people got the same answer. I should say the same wrong answer. I didn't want to leave you hanging there. A majority of you guys, though, let's see here. We got 1, 2, 3, 4, 5. Whoa! My ears. We got 1, 2, 3, 4, 5. We got 6 people with the right answers. Out of, what's going on here? I only have 11 people responding? 12 people responding now. Okay. Where's half of my class, guys? How come there's only 12 of you guys responding? You guys just trying to figure it out still? Do you not have enough time? Why is there only 12 of you out of, in here? We got 33 students in here, but yet I only have 12 people responding and only 25 people who are actually in the link to the Pear Deck. Are you guys not able to get into the Pear Deck? What's going on? Can you send the Pear Deck? Oh, Frankie, you're here. Hi. I think you typed into the chat because I saw you as absent earlier. So you're here. I got you now. Okay. All right. So that's the Pear Deck. Let's go ahead and start doing this and type your answer in, by the way. Get yourself some credit for today. That's how I'm keeping track if you're actually here doing work. All right, guys? So get into that Pear Deck. Actually type in some responses in there. Try it out. So how do I do this? What's the button that I'm going to be pressing? Well, the on button, first of all. There we go. Have this thing turn on, right? And how do I get to that screen where we type in the derivative? All right, hopefully you guys remember. It's math. Yes, Max. Good, good. You press math. What option is it? What option is it? Option 8. Oh, by the way, there's a shortcut for this. You know that thank you, Monica. Thank you, Shirley. You don't have to scroll all the way down here to press 8. You know that you can actually just press the number pad, number 8 on the number pad, and it'll take you to the same thing, right? So I'm taking the derivative with respect to x. Please make sure you put that in there. I know that that seems dumb, right? That it's blank to begin with, because you're like, you can type in whatever variable you want. It's just a feature that they have in there that you can type in other variables once we get to those types of problems. But just type in the x, right? And then we're going to type in our function x right here. Now, I guarantee you, some of you guys might have made this mistake. I guarantee it. I guarantee it. If you typed in x squared plus 2x divided by cosine of x, I guarantee this. A couple of you people typed it in this way, right? This is going to be wrong. This is going to be wrong. That's because this calculator is a little dumb. It needs the notations to know what's divided by what. If it types it in like this, it will take it by face value and say only the 2x is being divided by cosine. If you type it in like this, the calculator is going to think, oh, it's x squared plus 2x divided by cosine of x. And that's clearly not the problem. This does not equal to what we're working with. right? That is not equal to what we're working with, which, by the way, it is important, like I said, to write down exactly how you're typing it into your calculator, right? So what I actually need from this is to show that x squared plus 2x is on its own first. So I need to put parentheses around that entire function to show that it's the numerator, right? And then say divide by cosine of x. That way it knows to divide the whole thing by that, okay? This, of course, is still being evaluated at x equals to 7. So I'm going to go back into my calculator and fix that, by the way. So again, this is going to be messed up because it's going to think, oh, divide that whole thing. And some of you guys who are trying to fix it, you might notice that it is overwriting what you have typed. So what you can do is do second insert, and your cursor becomes an underline right there. So you can insert your parentheses wherever you need it. So I'm going to go ahead and do that right here. Second insert and do that right there. And if you don't want to do that, you can always just clear it out and just retype it out. See, the parentheses there will make sure that the x squared plus 2x is treated as the whole on the numerator divided by cosine of x in the bottom there. And this, of course, is at x equals to 7. I go ahead and press enter. Why is my answer wrong? It should be 94 point something. What did I do wrong here, guys? What's the common mistake that I need to make sure my calculator is set correctly? What should be set? What do I have wrong? Anyone want to type into the chat? What did I do wrong, guys? It's important. It's important. 16.25 is not the right answer. You're on degrees. That's right, Brian. I'm set in degrees currently. Shirley, that's right. Ava, that's right. It's in degrees, not radians. In calculus, please make sure you're in radians if you're in my class for calculus. If you go to your physics class, you might want to make sure and ask, hey, do we need to be in degrees or do we need to be in radians? Whoops, that's not what I want. Clear that out. I want to retype that entry. Let's press enter one more time. And that's my answer, guys, 94.045, right? My answer for this y derivative, the derivative of y evaluated at 7 is equal to 94.045,787. 458. Let's just go with that. By the way, how do you know how much to round up to or how much to round by? Usually like 3 to 4 decimal places is good. I try to say to go to at least 3 to 4 decimal places at the end. They don't usually dock you on that, but that's usually where the good cutoff is, 3 to 4 decimal places. Okay. I know that's way more than the 3 significant figures that you were taught, but that's just how it is in calculus. It just makes it easier to be safe. Better safe than sorry, right? Better safe than sorry. So yeah, that's that one. Okay. You guys doing all right with this lesson? You feeling okay? Feeling all right? Hopefully. Let's keep going then. Let's have you guys try this one. You don't have to type this into the, actually I should have did this slide. I don't know why I didn't. Can you guys go ahead and try this example? Let's see what you guys get for this one. Let's say I have here f of x is equal to x over x minus 2. And I want this evaluated at f, the derivative, at x equals to 2. So can you guys go ahead and try that real quick? Try that real quick. See what you guys get. See what you guys get. I wonder, actually, can I just add this slide in there and have you guys do it? Never mind. So yeah, I didn't put that slide in there, so I'll do that in the future. So try this out, see what you guys get. And I'm going to go ahead and get started on this here. So keying this in, again, we go math, right? We go down to option 8. We tell it that it's the derivative of x, with respect to x, I should say, the derivative of f of x with respect to x. And the function, if you're going to type this in, please make sure you have the parentheses around there again, right? So make sure you have this right. It's going to be x divided by, and in the bottom here, again, make sure you do this correctly. If you type in x minus 2, please understand, if you type it in like this, right, the calculator is going to think x divided by x first and then minus 2 on the end. I want the x minus 2 in parentheses because I want that to be done first. So it should be parentheses x minus 2. Please make sure you do that, or else it won't work out the right way. Right? So you got to make sure you do that. And then we're going to type in our value of 2 right here. And check this out. Our slope is, what does that say? 2,000,000, 2 million. The tangent line has a slope of 2 million. It goes up 2 million and then over 1. Degrees, not radians. Doesn't, oh wait, that's from before. But yeah, doesn't that seem a little odd to you? The slope of the tangent line right there is 2 million. Now that could be possible, right? That is possible. You could have a slope of a line, slope of a tangent line equal to 2 million, right? Equal to 2 million. But let's actually examine this one by hand first of all. Let's take a look at this guy, right? Let's take a look at this guy. So the derivative itself, if you do this by hand, right, is equal to low d high, the derivative of high is just 1, minus high d low, and the derivative of the low is just 1 as well, all over low low, right? All over low low. So the derivative here is going to be equal to, this right here is going to be x minus 2 minus x all over x minus 2 squared, which is going to give me this derivative right here, which is going to give me negative 2 over x minus 2 squared. And if I try to evaluate this derivative there, what do you guys notice at x equals 2? You end up with negative 2 over 0, which means the derivative is not defined at x equals 2. The derivative is not defined at x equals 2. And that's a big deal, by the way. The calculator, this is what I mean. The calculator is not a nice tool, but sometimes you need to understand that the calculator doesn't know how to do everything for you, right? We got the derivative to be equal to 2 million. That is not the case, actually. That's what the calculator says. So sometimes, you know, it gives you a number, it gives you an answer. But actually, though, what you should have spotted and said here is that f prime at x equals 2, right? Don't write it that way. Let's go with this. We're going to actually say it this way. F of x is not differentiable, meaning you can't take the derivative, is not differentiable at x equals to 2. So that comes into this whole new term right here, differentiability. Differentiable, right? Something that's differentiable just means that you can take the derivative of it, right? And certain functions are not differentiable at specific points, right? Some functions aren't differentiable at all, but may be differentiable at other points. But that's the new phrase we want to talk about here. Differentiability. Differentiability. So take a look here. The function that we were working with, this x over x minus 2, right? X over x minus 2. So f of x equals to x over x minus 2. I'm just going to give this to you right now. If you looked at this on a graph, right? If you looked at this on a graph, it would look something like this. At x equals to 2, you guys hopefully remember from chapter 1, at x equals to 2, we have a infinite discontinuity. Do you remember that phrase? Infinite discontinuity. How do I know that it's an infinite discontinuity? It's non-removable, and it's not a stepped function, right? It's a rational function. So it actually does something like this here. You have a vertical asymptote, and the function looks something like this. Something like that, right? Now, if you look there, right, my calculator said that the slope of the tangent line here was 2 million, right? If I drew a tangent line, they're saying that it's 2 million. That's because the calculator estimates as best as possible, right? It doesn't actually get it exactly at 2. It actually, what the calculator does is it gets a point that's close to 2, but not exactly 2. It gets it really close to about, I'd say that what it gets close to is about like, when we do it by hand, we're doing it as h approaches 0, right? What the calculator does is it gets really, really close, and it gets h to about 0.0001. It gets as close as it can, and it uses that as its estimate. So it's actually not evaluating it at 2, right? It's not actually evaluating at x equals 2. It's actually evaluating it closer and closer to 2.0001, which is right about here. And it's super, super steep. It's so steep, actually, that it gives you that slope. Right? It actually does it from this side as well. It gives you that slope of 2 million, right? It gives you that slope of 2 million. But looking at this, right, seeing that this function is not continuous, that actually just tells you right there that this function, right, f of x, is not differentiable. That's all I would say. Is not differentiable at x equals 2. It's differentiable everywhere else, by the way. It's differentiable here at x equals 3, at x equals 1, right? I can see my tangent line there, and I can calculate the derivative there. But it's not differentiable at that point, x equals 2. Okay? It's not differentiable there at that point at x equals 2. So, check this out. Let's say I have, for example, a function. Let's keep going here. Let's say I have here, for example, a function f of x equals to the cube root of x. Right? F of x is equal to the cube root of x. Can you guys, right now, can you guys try to find the derivative of f of x evaluated at 0? Can you guys go ahead and try that? Calculate the derivative at f of x of the cube root of x at x equals to 0. Can you guys go ahead and try that? Ooh, excuse me. Go ahead and try that. See what you guys get. Try it on the calculator. See what you get on there. Try it by hand. See what you get by hand. See what happens. We can go math, option 8. I'm going to take the derivative with respect to x. Oh, do you guys know how to type in the cube root of x, by the way? Do you guys know how to do that? Any ideas? No. Math, and then option 4. That is one way. Yes, that is on math and option 4 is right there. That is one way you can do it. And you can see the cube root goes in there, x, right? You can do it that way. If you do a 4th root or a 5th root, right, you can do exactly what Kaylee's saying right there. You could rewrite the function as an exponent, which is what you're supposed to do for some of your homework when you're using the power rule. So make sure you have that down, right? Radicals can be written as this, right? And Ava's already in there saying that she got undefined. Let's take a look here. Boom. Wait a second, you got undefined. I got a value. It is undefined though, by the way, Ava. It is undefined. The derivative does not exist there. My calculator, I have a different calculator. You have a better calculator. That's actually a better value. My calculator is giving me 100. It's actually not 100. I know some of you guys are like, but doc, I also got 100. It's actually, let's take a look at this by hand. By the way, if you select 100, you'd actually would get this wrong, even though your calculator says it's 100. And here's why. You ready? Try doing this function by hand. Try doing this derivative of this function by hand. You'll get 1/3 x to the negative 2/3. Right? That's just the power rule. Hopefully you have been practicing that. It's going to be the power comes down, and then you do 1/3 minus 1, which comes out to be negative 2/3. You ready for this? Simplifying this out, this is going to be 1/3 times x to the 2/3 in the denominator because it's a negative exponent. So that pushes the x down into the denominator. When you go to evaluate this at 0, you end up with 1/3 times 0, which ends up being 1/0, which is undefined. And what does that tell me? That tells me that f of x is not differentiable at x equals to 0. That's what that tells me. And that's what you got to be able to pay attention to and be careful about it, right? It's not differentiable there. But what does that look like? What does the cube root of x look like, and why is it not differentiable there? Well, let's take a look at the cube root of x and look at it at x equals to 0. How do you type the cube root of x into Desmos? I go like that, and then can I modify the power? No. Do you go into functions? There it is, the nth root. So just like on your calculator, there should be a function here, and it looks like it's under functions, under miscellaneous. I'm looking for the nth root, so it gives me a little option right there, and I can type in the root, the power of my root. That's not the right word. I should know the word, but I forget right now. But anyways, the cube root of x, and it looks like this. See that? And you'll say, Nagmi, it looks like the derivative here exists at 0. It looks like it exists. The derivative here does look like it exists. But what type of tangent line is there at x equals 0? Can you see it? What kind of tangent line is there? As I come over here, the tangent line over here would be kind of slanted. But right at x equals 0, what kind of tangent line do you have there? I hope you can see it. It's vertical, right? The tangent line. Mine says not a number. Oh, good, Aurelia. Yeah. Oh, you're also in here, Aurelia. I swear you weren't in here earlier, but you made it in here. Not to call you out, but just double checking my attendance roll. Good, you are checked off. The only person I have missing, by the way, is Julia. I'm confused on how to type a cube root into the calculator. Let me show you. So if you ever need to type a cube root, you could do what was shown earlier by pressing math, and the cube root is right there as option 4. But what I'm saying is, though, you don't have to type it that way. What I'm saying is you could actually just type it using, using the power rule. So I could do it this way as well. I can say, let's go math, option 8, x, and I'm going to go in here and type in x to the power, right, to the power of 1/3. That's actually the same thing as a cube root, Frankie. So that will make it a little bit easier to see. Evaluated that at 0. Now, again, these calculators are giving us values, but I'm telling you right now, that is not the actual case, right? So this calculator is failing us at this point, right? And I need you to understand why, right? When you look at this graph, right? Remember, what is the derivative? The derivative of the slope of the tangent line. And the tangent line at x equals to 0, the slope of the tangent line at x equals to 0 is undefined. The slope is undefined there. How do I know that? If you look at the tangent line there, it is a vertical line. It is a vertical line. You see it? Right there. That purple line right there is the tangent line. And its tangent at that point is x equals 0, and the slope of that line is undefined. So this function is actually not differentiable at x equals to 0. It's differentiable everywhere else except for that one. Right? It's differentiable everywhere else except for that one. Let me show you what I mean. Let me open up this real quick here. Get into my derivatives here. So let's take off that. Let's take off that. No, let's keep that there. Take that off. Here's something that will draw a tangent line for you for your function, yeah? Well, let me show you the function we were just working with, which is going to be the cube root of x. So this is the cube root of x. That's what the function looks like. And again, if you're looking at this, right, the tangent line looks like it exists everywhere. And it also exists right there. But this calculator is having trouble drawing that tangent line because that tangent line is vertical. That tangent line is vertical. So that slope there does not exist. A slope of a vertical line is undefined. Right? A slope of a vertical line is undefined. It's because it's something over 0. It's going up infinitely, and it never crosses. So that tangent line right there, boom. See it? So that's what, by the way, something that's not differentiable. So you can actually see these now. So some functions will be differentiable at certain points, and some functions will not be differentiable at other points. Okay? So when are things differentiable? When are they not differentiable? Well, that's a couple examples right there that I wanted to show you, right? When there is a asymptote right there, the function is not differentiable, right? If the function has a tangent line that is vertical, it's also not differentiable there because the derivative does not exist there, right? And last but not least, right? So far, we've looked at these things, and one of the big things it looks like, oh, if the function is not continuous, it looks like it can't be differentiable there, right? But just because a function is continuous doesn't necessarily mean that it's differentiable, right? This is one proof of that. This is a continuous function. The cubed root of x is a continuous function all the way through. There's no holes here. But it's not differentiable at x equals to 0. It's not differentiable there because you get that vertical line. So that's one example. Another example I wanted to show you of something that is not differentiable is a function that looks like this. Let's say I was looking at, let's say f of x was equal to the absolute value of x squared minus 3x plus 2. You guys write that down? The absolute value of x squared minus 3x plus 2. Okay. This function is continuous. I hope you would agree with that. X squared minus 3x plus 2 is a parabola function, which is continuous everywhere, right? The absolute value, though, makes it look a little weird, right? Makes it look a little weird. So hopefully you guys got that down. If not, I'll put that back up in a second. Let's go back to a blank calculator. This is the function right here. Absolute value of x squared minus 3x plus 2, right? So let's take a look here. Let's take a look at what that graph looks like. The absolute value of x squared minus 3x plus 2. So that's the graph of this parabola right here, right? That's the graph of this parabola right here. And here's the thing. This thing is continuous. You guys see that, right? It's continuous all the way from negative infinity all the way up to infinity. But derivatives help you calculate the slope of a tangent line, right? Now here's my issue. When you look at this thing, the tangent line here is perfectly fine. If you're looking at like 2.5, you can see that tangent line. You can imagine it, right? You can also imagine the tangent line over here, right? You can get the slope of the value of that tangent line. Same thing with everything in between 1 and 2. You can see that right there. But look closely at, let's just look at one of these points, either 1 or 2, right? Let's look closely at 2, for example. Remember, when we calculate these derivatives, you're thinking to yourself, right? It's the limit as one point gets closer to another point, right? And you're calculating the slope between those two given points until it reaches 0. So if I approach the limit and I calculate the slope of the tangent line as I approach it from the left-hand side, right? We keep coming back to these limits, guys, I'm telling you. And I'm taking the limit as I approach it from the left-hand side, I get this negative slope right here. You see that? And it's actually getting increasingly more negative. It's getting steeper and steeper in the negative sense. On the right-hand side, it's a positive slope as I get closer and closer to 2. They don't approach the same limit as they approach 2, right? As I get closer and closer to 2 over here, the derivative is getting more and more negative. The tangent line is getting more and more negative. As I approach it from the right-hand side, the tangent line is getting more and more positive. So as I get closer and closer to this guy, right, this thing is not differentiable at x equals to 2, right? It's not differentiable at x equals to 2. If I were to zoom in, right, at x equals to 2, I get this thing right here. I get a little point. I get a little pointy thing right there, right? That's called a corner. And derivatives do not exist at corners. So I would say here, the derivative at 2, right? This is not differentiable because of that corner. That's what I would say. So functions are not differentiable when they're, discontinuous. So if there's like a hole or an asymptote, the derivative does not exist there. But if it's discontinuous, it can also not exist at these corners, right? If you have a function that has a corner, it's pointy, right? The limit when you come from the left-hand side does not equal to the limit when it comes from the right-hand side. So it's not differentiable at that said corner. Where else is it not differentiable? Let's take a look at another example. Let's say I have here g of x was equal to x to the 2/3, right? X to the 2/3. By the way, if you're given this problem in the book, they'll probably write it like this, as the cube root of x squared. And if you want to know how to type it out as your own function, I would use the exponential instead. So let's take a look here real quick at x to the 2/3. Okay, x to the 2/3. So let's take out this function. Right, and let's type in this function right here. F of x is equal to x to the 2/3. And look right here. X to the 2/3 is a continuous function from the left-hand side all the way to the right-hand side. And you'll see right here, it's pointy right there. And it's the same concept. If I have a tangent line and I keep coming from the left-hand side, it's getting more and more negative, right? It's going more and more negative. That tangent line, the slope of that tangent line is going more and more negative. If I come from the right-hand side, that slope is becoming more and more positive. That slope is coming more and more steep on the positive sense. And as it approaches 0, right, as it gets closer and closer to 0, right, this is going to be more and more positive. This is going to be more and more negative. The limit from the right-hand side approaches positive infinity as a slope. And this one over here approaches negative infinity as a slope of that said tangent line. So right here, this is the same thing. I would actually say that this right here, when you graph this, right, looks like this, right? That point right there at x equals to 0 is also not differentiable. Not differentiable there. And when it's not differentiable there, right, that just means you can't calculate the slope of the tangent line at that point. And I hope you guys can realize this, right? If you think about a tangent line, right, it's just this thing that touches at a single point, right? So there, right, or here for, that's terrible tangent line, right? Or like here, for example. When you go to this cusp, that's what this is called, by the way. You can draw a tangent line like this. You can draw a tangent line like that. You can draw a tangent line like this. At a cusp, there's just too many ways to draw that tangent line. So we can't actually calculate the derivative there. We don't know which tangent line, which slope that we're looking at, right? So we say that that's not differentiable. And we call this guy, right, I just said, this is a cusp. This is a cusp. So on the AP exam, if you're looking at something and they ask you, hey, does this graph look like it's differentiable? And you ever see a corner, a cusp, right? We say that those things are not differentiable. And the reason we give it is we use this word right here called local linearity. Local linearity. Local linearity. These two guys do not have local linearity, right? If it does have local linearity, the derivative exists there. Let me show you, right? How do I know if something is differentiable? If you zoom in enough, you should see it turn into a line at that point. So let's take a look over here. Let's take a look at another function. Let's say one function we were dealing with earlier, which was like 2x to the third plus 5x, I don't know, minus 10, right? And it looks like this function, right? That's not fun. Let's go with 5x squared. There you go. Minus 10x. That's even better. So let's take a look at this function right here, right? This one has a bunch of curves. How do I know that it's differentiable at a point? So what I'm saying is if it's differentiable, it will contain local linearity. And what I mean by local linearity is if you zoom in enough at any given point, that function will be a line. And if you don't believe me, you should try this yourself. I've just zoomed in at a random point right here, but look what happened to my graph. This is what I mean by local linearity. If you get in close enough, it turns into a line. But you know this function is not a line, but that's what I mean by local linearity. If you get in close enough, it looks like a line. See that? And that's going to be true at any point on this function. So if I get over here and you say, Nakmi, is that true over here? It's even more so over here if you zoom in right here. Look at this, right? That looks more like a line right there. And that's what I mean. It's differentiable if it has local linearity. If there is no local linearity, much like the cusp that we graphed earlier, the 2/3, take a look at this guy. Hopefully you're not getting a headache from this. Has local linearity here, has local linearity here, but if I go to where x is equal to 0, where I'm telling you it's not differentiable, look at what's happening as I get closer and closer. It's not a line, right? There's no local linearity there. That's why it's not differentiable there, okay? So keep that in mind. If I ever ask you if something is differentiable or not, keep an eye out to see if there's any local linearity. And basically, if you have a corner or a cusp, you would just say not differentiable, no local linearity there. If you have something that has an asymptote there, that rule still applies, by the way. There's no local linearity there. You zoom in on that thing never touches, and you actually can't draw a straight line for that function at that point at x equals 2, wherever you have that. Okay? All right. You guys doing all right? You guys doing okay? Are you completely like, what is going on? Or are you feeling all right? This is more of the conceptual part of calculus, right? You can still do derivatives, right? I'm still going to ask you to calculate derivatives for me. You're scared? Don't be scared. Don't be scared. It's not. I know it seems bad, but it's one of those things that, like, you have to understand that just because you have these rules where you can take the derivative, right? Like, I give you a function f of x, and I ask you guys to take the derivative of, let's say, x squared plus 2 over 3x. You guys have the skills to do this now, is what I'm saying, right? If I ask you to take the derivative of this, you guys will be able to do low d high minus high d low over low low. You'd be able to do this with no problem, right? You have the ability to do this no problem. You guys see this, right? Like, if I gave you a problem like this and I asked you to find the derivative, you'd be able to tell me that this is the derivative, right? All I'm asking from you right now is to understand that you can't evaluate that derivative at every single x value, and you need to be okay with that. And if that ever happens, you need to be able to tell me, hey, you know what? At x equals to 0, f of x is not differentiable. And I hope you guys can see that. Why is it not differentiable there? Why is it not differentiable there? That's because if you plug it in, you get something that's undefined, right? That's one way of doing it algebraically. Graphically speaking, if you were looking at this function as a graph, at x equals to 0, this thing is not continuous, right? It's not continuous at x equals to 0. It would look something like, I actually have no idea what it would look like, but I would have an asymptote there. And I would say that since it's not continuous, right? Not continuous, it's not differentiable there at that point, right? Or if you have something that you're looking at a graph, sometimes there will be a problem where they don't even give you a function written out algebraically. They'll just give you a graph and it looks something like this, right? That's terrible. I could draw a better graph. Hold up. Oh my God, knock me. Just, right? And you'll be able to tell me this function is differentiable everywhere except that point, and you'll say verbally or written, you'll write down a sentence, not differentiable, right? Not differentiable because what? Because it is a cusp, and therefore a cusp has no local linearity. That's the new word that I want you guys to remember for this one, by the way. Local linearity. Something is differentiable is if basically, if you get nothing else from this, basically, if you zoom in enough, right? If you zoom in enough, you'll see a line, right? The tangent line does that because when you get to that one point, it only touches that one point, it forms a nice line. If it doesn't have local linearity, when you zoom in, it still doesn't form a line, right? So if you take a look at this problem right here, let's actually move this over real quick. Let's say it was x minus 1, right, to that power. So let's take a look at it and let's move it up so we can see it a little bit better here. So check this out. If I looked at this point right here, right, how do I know that this is not differentiable at x equals to 1? How do I know it's not differentiable at that point, right? When I learned this, I didn't have the phrase local linearity. When I learned this, I actually literally called that a pointy thing. It's not differentiable at pointy thing. And that was acceptable back in the day. You can just say it's pointy. It's not differentiable because it's pointy, right? Same thing with the absolute value function, by the way. If you did the absolute value of x minus 1, right, plus 0.5. If you look at this black line right here, right, same thing. You would say that it's not differentiable there at x equals 1 because pointy, right? Better word. No, Max, that's not the better word. But again, this is what I'm trying to say. You still need to be able to identify, hey, It's not differentiable at x equals to 1. Why not? Because there's no local linearity there, right? If I keep zooming in, hopefully you guys aren't getting dizzy when I zoom in that fast, but you see, no matter how much I zoom in, I'm zooming in quite a bit, by the way, so much so, and there's still no local linearity there. It does not turn into a line. Whereas if I were to graph something that looks like this, 1 squared plus 0.4, let's say, and I was looking at this line. I zoomed in so much. Give me a second there. Boom. You see this red line, this parabola. It is differentiable there. It is differentiable though. Even though this tangent line is approaching 0, this tangent line is also approaching 0 as I get to this point right here. And I kid you not, you zoom in on this red line enough, it turns into a line. And that's what local linearity is. If you're still struggling with that phrase, that's all local linearity is. You zoom in enough, what happens to the red line? You ready? It becomes straight. And that's all local linearity is. And that means that it is differentiable at any of these points that I zoomed in on. Whereas if I'm looking at something that's pointy, this corner, for example, when you zoom in, no matter how much you zoom in, you still don't have any local linearity. You still don't have a line there. You'll say, knock me, there's 2 lines. I don't want 2 lines. I want a solid line, just a single line. Local linearity. Okay? That's that. So that's part of that. I took way too long on this, and I didn't get to the next part of the lesson, but that's okay. Differentiability is an important thing that you need to be able to identify if it is differentiable or not. And if it's not, why is it not differentiable? All right, guys, I'm going to stop there for today. I was trying to get to another section, but spent too long on this one, but that's okay. Hopefully you guys have a better understanding of it. And if not, stop by my office hours. We can talk more about it, but that's going to be it for today, guys. We'll continue our lesson on 2.5 on Thursday, where we're going to talk about the connection between derivatives and position, velocity, and acceleration. All right, that's it for me, guys. I'll see you guys later. Have a good rest of your day. So long, guys. Farewell.